For decades, astronomers have searched for Planet 9, but what if it was already recorded and no one noticed? Recently, a quiet development has pushed this debate into a new phase. Not because someone pointed a telescope at the right spot and found a planet, but because astronomers went back into old data and noticed something incredible. Two infrared sky surveys taken 23 years apart show a faint source that appears in one and then in another place decades later. And suddenly, a question that's been asked for years has to be asked again, not in theory, but in data. What if Planet 9 was already there? The Planet 9 idea didn't begin with images. It began with motion. In 2016, astronomers Michael Brown and Konstantin Batygin were studying a group of extreme trans-Neptunian objects, small icy bodies orbiting far beyond Pluto. These objects weren't randomly oriented. Their orbits were clustered. Their perihelia pointed in similar directions. And statistically, that clustering wasn't easy to explain by chance alone. The simplest explanation was gravitational. Something massive, distant, and unseen was shepherding those orbits into alignment. Not a star, not a passing object, but a planet several times the mass of Earth on a long, eccentric orbit hundreds of astronomical units from the Sun. That idea became Planet 9, not Planet X in the doomsday sense. Not a rogue intruder about to disrupt Earth, but a cold, distant world whose gravity quietly shapes the outer solar system. The problem was obvious. If Planet 9 existed that far out, it would be incredibly faint. Too far to reflect much sunlight, too cold to glow brightly. Traditional optical searches might miss it entirely. A planet doesn't need to shine to be seen. It only needs to be warmer than absolute zero. Even a cold, distant planet emits a small amount of thermal radiation, especially in the far infrared. That makes infrared sky surveys one of the best tools for detecting distant, cold objects that optical telescopes might overlook. And this is where two older space missions re-enter the story. In 1983, the infrared astronomical satellite, IRAS, performed the first all-sky infrared survey. It wasn't perfect. The resolution was limited, but it mapped the entire sky in infrared wavelengths. More than 2 decades resolution. Together, these two missions created something rare in astronomy, 2 full-sky infrared snapshots of the same universe, separated by 23 years, and that time gap matters. Because a planet hundreds of astronomical units away would move slowly, but not imperceptibly, over 2 decades. When astronomers compared IRAS and AKARI data, they weren't looking for a dramatic reveal. They were looking for subtle inconsistencies. Faint infrared sources that appeared in one survey and then showed up slightly displaced in the other. And that's when one pair stood out. In the IRAS data, a faint infrared source appears at one location. In the AKARI data, a similar strength infrared source appears nearby, but not in the same spot. The measured angular separation between these two positions is about 47.4 arc minutes. That number isn't dramatic by itself. But when astronomers calculated how far a distant planet at roughly 500 to 700 astronomical units should move over 23 years, the result was uncomfortably close. Too close to dismiss outright. Too clean to ignore. Importantly, the IRAS source is not present at the AKARI position, and the AKARI source is not present at the IRAS position. This rules out many common explanations, like variable stars or transient noise. Researchers also checked for nearby fast-moving objects. Hour-by-hour parallax effects were accounted for. Anything close enough to Earth to fake this motion would have revealed itself quickly. What remained was a slow mover, a cold emitter, and a candidate that fit more criteria than astronomers expected. The analysis was led by Terry Long Fan and colleagues at National Tsinghua University. Their work didn't announce a discovery. It didn't claim confirmation. Instead, it did something far more cautious and far more disruptive. It presented a candidate. The team identified a possible pairing between IRAS and AKARI. Both sources show consistent far-infrared flux levels. Both appear isolated, and both sit in positions consistent with slow motion over decades. Based on the infrared emission, the object's estimated mass could exceed that of Neptune, around 17 Earth masses, depending on assumptions about composition and temperature. The estimated temperature range, roughly 28 to 53 Kelvin, matches predictions for a distant ice giant far from the sun. This wasn't proof, but it was alignment. Alignment between prediction and observation. And in astronomy, that's often where discoveries begin. At this point, it's tempting to jump to conclusions, but astronomers haven't, and that restraint is important. 2 data points do not define an orbit. They suggest motion, but they don't prove gravitational binding to the sun. Infrared surveys are crowded. Galactic dust structures can masquerade as point sources. Differences in instrument sensitivity and beam size can produce misleading matches. There's also the issue of WISE, NASA's Wide Field Infrared Survey Explorer, which does not show a clear detection at the expected position. But that absence isn't definitive either. A moving object could easily fall outside WISE's detection window or be confused with background emission. In other words, this candidate hasn't been confirmed, but it also hasn't been eliminated. For years, the Planet 9 debate has been stuck in a holding pattern. Predictions existed, candidates appeared and faded. But the observational tools weren't quite capable of delivering a decisive answer. That's changing. The Vera C. Rubin Observatory is now operational, scanning the southern sky repeatedly with unprecedented sensitivity. Its wide field of view and repeated coverage mean that slow-moving objects at extreme distances can finally be tracked over time, not guessed at, but measured. If a Neptune mass object exists at 500 to 700 astronomical units, Rubin should see it. If not immediately, then within a few years. Other instruments, like the Dark Energy Camera, can also conduct targeted follow-ups. For the first time, the Planet 9 hypothesis is testable in a practical, observational sense. This IRAS AKARI candidate didn't emerge too late. It emerged at exactly the moment when confirmation or rejection is finally possible. If this object turns out to be Planet 9, it raises an even bigger question. How did a planet that massive end up so far away? One possibility is scattering. In the early solar system, interactions between the giant planets could have flung a growing ice giant outward, where it settled into a distant, elongated orbit. Another idea is capture. The sun may have passed close to another star early in its history, stealing a rogue planet in the process. This sounds exotic, but simulations show it's not impossible in dense stellar nurseries. More speculative ideas exist, including primordial black holes, but those lack strong observational support and remain fringe explanations. What matters is that standard planetary physics can still explain Planet 9, if it exists. Right now, Planet 9 sits at a crossroads between possibility and proof. The IRAS-AKARI comparison doesn't confirm it, but it sharpens the search, it narrows the sky, and it gives astronomers a concrete target rather than an abstract prediction. Over the next few years, surveys will either find a slow-moving, cold object where models predict, or they won't, and either outcome matters. If Planet 9 is found, the solar system instantly becomes larger, more complex, and less tidy than we thought. If it isn't, then something else must be shaping the Kuiper Belt, and that mystery will remain. So where does that leave us? With an image that refuses to be dismissed, with data that aligns too well to ignore, and with tools finally capable of delivering an answer. Planet 9 has not been discovered, but it also hasn't disappeared. And for the first time in decades, the question isn't whether astronomers believe in it, it's whether the universe is about to stop keeping the secret.